The camera disappears. The audio disappears. Okay.
The audio was us.
So let's see if we can share the Blackboard here. Take a second. Okay. So let's see if I can do that. Oh, I have to. Okay, so now it should be sharing the screen. I have to rearrange a couple of windows, and then we get going. Okay, so here we go. Okay, so what are we talking about today? So today, we're going to think about circuits of neurons. If you build circuits, you probably build circuits out of logic gates or transistors, for those of you who build circuits. And in our brain, let's get a better color. In our brain, our circuits are built out of neurons. And so we would like to understand those circuits. Uh-oh. There we go. Okay, so if we look inside a brain, what do we see? We see a lot of neurons. They're super tiny. You can only see them with a microscope. And then you try to trace out how they're connected to each other, and it's a big mess. Right? It's not some very clear, easy, it's not like looking inside your building at all the pipes carrying the water, and you can figure it out, right? You see where the clean water comes in, the dirty water goes out, and you see how the pipe's distributed, and it makes sense, right? But when you look in the brain, you see all these neurons, all these axons connecting to dendrites, and it's like a big bowl of spaghetti, and it's not clear how it's working. So people do experiments, sticking an electrode into the brain, recording from cells, studying single cells in a dish or in a slice, trying to figure out how the neurons work. And you can figure out some things, but it somehow feels descriptive until you try to build systems yourself. If you want to understand the technology that evolution discovered that allows it to build brains, then we have to try building things and see how that works. So if so we don't know how to build something like a brain. We do know how to build something like a computer, which is like a brain in some ways and not like a brain in some ways, right? Computers can do things that before computers required brains, like multiplying 536 times 254, right? That you needed to find someone who had learned how to multiply, who'd gone to school, and they could tell you the answers to questions like that. So if you were going to sail on a ship and you're going to, try to go far away, you'd have to get one of these people who had gone to a lot of school to come with you on your ship and who knew how to make measurements with the stars and turn that into, some estimation of where you are on your map. Right. So these sorts of things used to be jobs for people, and now, of course, we have computers and automated systems built out of the same technology as we use for computers to do all these things for us. Okay, so but there's a lot of things we do that computers don't do. Computers are good at calculating, right? That's what they were made to do. They calculate things, and they do that very well. They do that much better than people do it, but that's pretty much all they do, right? the idea of the computer, the Turing machine from Alan Turing, was created as a machine for doing calculations. And the idea of an algorithm came from how people do calculations. So all of the thinking that led into computers came from how to do calculations, and the computers are great at doing calculations. They're much, much better than people at that. But for things that aren't calculations, then we don't know exactly what we're supposed to do, and we haven't been able to build machines that just do ordinary day-to-day reasoning. Like there's a dog barking outside my door. What should I do? Right? Should I give it some food, or what should I do? Right? These sorts of things that's not a calculation, and we don't know how to make them. We don't know how to automate it. So let's look at a little more concrete comparison. So let's suppose we have suppose we're doing things with digital logic, then we use AND gates, OR gates, NOT gates, right? So an AND gate, I'm just going to draw all the gates like this with some inputs and an output. There can be some number of inputs and an output. A NOT gate is funny, you can only have one input and one output. All right, we can put a little arrow to make it clear. Okay, and how do these gates work? So we're talking about digital logic, so we have ones and zeros. So these little lines sticking out of the circle is the gate. That's like a little function. It's a function that evaluates its answer. And the inputs are ones and zeros. And what does that mean? So we think of these lines here are like wires, and the ones and zeros are the values on the wires, like high voltage or low voltage. And so then what does the gate do? It produces an answer. So the AND gate, how does the AND gate work? It looks at all of the inputs and it sees if they're all one. If this is one, and this is one, and this is one, and this is one, then the output will be one. But that's not the case here. They're not all one, so the output here would be zero. In digital logic, one is like true, zero is like false. If we have an OR gate, let's say we have a couple of inputs, 0 and 1, then what would the output be? Well, it's like the AND gate, but now we're doing OR. So we ask, is the top one 1, or is the bottom one 1? And then the answer is yes, because the bottom one is 1. And the NOT gate, it just like the name, if it receives some input, say 1, then the output is not whatever the input was. So not 1 is 0. That's the only other value. If it receives a 0, then not 0. The only thing that's not 0 is 1. So that's the NOT gate. So we can say which gate we're using like this. If you look in the book, they have very nice, slightly different shapes for all the different kinds of gates you might have. But it's easier to keep track of if we just write the name in it. Okay, so if you think about the AND gate, right, it only gives an output of 1 if all of the inputs were 1. So what's an example where the output would be 1? Well, in fact, there's only one example. Here, if we have 4 inputs, all of the inputs have to be 1. Doesn't really depend on the number of inputs. They all have to be 1. How about an OR gate? An OR gate is usually, it's usually 1, like it was here, right? Because if any of the inputs are 1, you get a 1. So can it ever be 0? Of course, it can be 0. So how can it be 0? It's kind of like the opposite of the AND gate. It can only be 0 if there weren't any 1s among the inputs. So if all the inputs were 0, then it produces a 0. And that's the only way it can produce a 0. So it's kind of like an AND gate, but with the ideas of zeros and ones flipped. Okay, so these are the gates we use in digital logic. We build up circuits with those gates, and there's a whole theoretical technology of how to make a circuit that does whatever you want. For example, to multiply 2 numbers, how would you make a circuit of these gates? So that's a theoretical technology, and there's a practical technology where we know how to turn those circuits into transistors, and we can actually build a device which will multiply those numbers for you. And then, yeah, that's very convenient. And then you can build these devices and you can sell calculators. And yeah, that's useful. So we'd like to understand something about brains. So what, right, brains don't have wires. Well, they sort of do. They have axons, right? the dendrites are more, the axons are the most like wires. They're very thin, they go a long way, they carry a signal, but the signal they carry is somehow localized in space. It's different from if we build an electronic circuit and we, for digital logic, things aren't localized in space. If you want to build an antenna, then yes, space will matter. Okay, so if the only ideas we have available are the ideas of digital logic and how to do calculations by reducing them to logic, then how would we think about how the brain might do calculations? We might imagine that the brain reduces calculations to logic. So people don't really think this these days, but back in the 1940s, this is how the ideas got started. People were thinking, even computers were a very new thing. You had to, you would have to be in the right place at the right time to actually see a computer somewhere, and it would be a huge object filling a room. So, but they were very inspiring because they actually did work that previously could only be done by brains, right? There had been the Industrial Revolution creating machines that could do work that previously required muscles, but there hadn't been a substitute for brains until computers were developed. And suddenly work that had previously required people whose brains had been trained to do various kinds of calculations, suddenly all of that could be automated. And so people thought, this must be how brains work. They must work in the same way that we're building computers. And so let's try to understand brains in terms of digital logic. Okay, so how would we do that? So I said that this idea, so the motivation that brains must work by doing digital logic, this motivation is left over from the 1940s, but the ideas that it led to are still used today. So let's look at what those ideas are. So suppose we try to build a unit that's kind of like a neuron. Maybe some kind of abstraction of a neuron, right? And if we want to think of digital logic, then what would the output be? Well, we can imagine spike or no spike, but that's very temporary. It's transient. You can't hold an axon up at the spike level, right? If a spike is 1 and no spike is 0, then anytime a wire goes to 1, it goes right back to 0. So that doesn't really work for building digital logic. So how else could we think about 1 and 0? Well, when you're recording from neurons, often you find that you'll find a neuron that's active, right? If you record from visual cortex, you'll find neurons that are active when they see a moving line in a certain position. And at other times, for example, when they don't see the line, the neuron is not active. So let's think of these as the two states of the neuron, right? The neuron is perhaps seeing what it likes and it can respond to it, or it's relatively inactive, right? So let's use this as our analogy for the abstraction. And a neuron can have a lot of inputs, right? They actually typically have many more inputs than the logic gates. For logic gates, here actually I drew more input. People often use just 2 inputs for the logic for and or, like this one, had just 2 inputs. That's a very common way of using and or gates. And it doesn't really matter whether you restrict yourself to 2 inputs or use more inputs, because you could, right, if you have, let's say we have a little chain of AND gates like this. So this is a circuit where the output of some gates feeds into the next gate as an input, right? So that's all. When we say a circuit, that's all we mean. That some gates are wired together so that they send their information to each other. Okay, so now what does this circuit compute? It has 4 inputs, 2 over here, one in the middle, 1 near the end. But if we provide all of these inputs, right, if we provide these 2 inputs, then the first AND gate can compute its output, and so then the second one knows both of its inputs, it can compute its output, the third one has its inputs and can compute its output, right? So if we supply all 4 inputs, then we're going to get an output. And what would that output be? Right, what function is this computing? Is it doing something interesting? Is it adding numbers? Well, we could ask, for example, how would it be possible, say, for the output to be a 1? right? That was the case that with this AND gate, we knew if the output was a 1, we knew all the inputs must be a 1. So
Matt.
here, if the output is a 1, then we know the inputs must be a 1. This must be a 1, and this one also, which means the output of this gate was 1, which means its inputs had to be 1, and so on. And so we see that, in fact, if the output is 1, all 4 of these inputs have to be 1. And which means that for any other combination of inputs, the output would be 0, right? Because we know if the output is 1, then the inputs had to be like this. And so, in fact, this circuit here is equivalent to this AND gate here with 4 inputs. So if you let yourself have a lot of inputs on your AND gates, then you can draw your diagrams like this. If you only let yourself have 2 inputs for an AND gate, then you have to draw the circuits like this when you want to do an AND of more than 2 inputs. So that's why it doesn't really matter. If you have these available, you can use them. If you don't have them available, you don't really need them, because you can use this 2-input AND gate. Okay. But when we look in the brain, we see neurons have thousands of inputs, kind of a lot. Certainly not like the circuits we make, not like the digital logic circuits we make. Okay, and then so how does a neuron decide if it's active or inactive? Right, if you have thousands of inputs, there are all kinds of functions you could compute, right? You could have a 64-bit multiplier would just be a tiny, it wouldn't need, that would only need 128 inputs. What would you do with thousands of inputs? Well, actually, we don't think a neuron can do something like a 64-bit multiplier. A neuron is very simple, right? So if it receives an active input, what does active mean? It means spiking a lot. So what happens at a synapse where there are a lot of incoming spikes? Say you're a neuron, and on your dendritic tree, you have a lot of synapses. And say at one of those synapses, there are a lot of spikes coming in from the presynaptic neuron. So what does that do to you? Well, each little spike makes a little EPSP, right? An excitatory postsynaptic potential, has a little time course. It's very small, right? I'm talking, maybe a millivolt, and it's pretty brief, maybe a few milliseconds. By the time the pulse gets to the soma, it's kind of widened out because the dendritic tree, right, it's not propagating that information as a spike, but just as a general voltage level. And so it doesn't have a big effect. A single spike coming in doesn't have a big effect. But if there's a synapse with a lot of spikes coming in, then what's happening? That means there's kind of a steady amount of current coming from that synapse, right? And this current, if you think of yourself as a neuron with some leak across your membrane, if you have some incoming current, then it's going to raise your voltage level, right? The membrane voltage is going to go up depending on how many, depending on how many synapses have active spiking neurons sending you their spikes. And it also depends on, say, the strength of those synapses. So if we look at let me draw an example with fewer inputs, just so I can draw it, okay? So then on these inputs, we can also have 0 or 1, depending on whether that input was active or inactive. And then what's going to happen? If we think of the current coming in, if the current coming in is low, then it will just drain out through our leak. But if the current coming in is higher than our leak can drain it out, then the voltage is going to build up until we spike, and that resets the current, but then it's going to build up again, we'll spike again. So if the current is above some threshold, then we're going to start spiking regularly, and which is what we mean by active. So let's, right, we could describe this in more detail and make it more complicated, but here we're trying to make it simple, to simplify and get some very simple abstraction. So what do? We say, well, different synapses probably have different strengths depending on how many receptors there are for the neurotransmitters, how much neurotransmitter is getting produced on either side, how much stuff is getting put in the vesicles, how quickly, how likely a vesicle is to get released. There are all kinds of factors that come into play, but here we can just simplify that all into there's some kind of effectiveness of that synapse. If the neuron is if the presynaptic neuron is active, then there's some effect that's going to have on us. And we call that the weight of the synapse. It's the strength of the synapse. So each synapse has a weight, which is a real number. So our neuron, our artificial neuron is being characterized by some real numbers here, which we didn't have for our digital gates. And then we want to see if we reach some threshold. So we add up the weights for the active inputs. So for example, if let's see, if this input was active, and this was inactive, and this was active, then our model for the current coming in would be W1 plus W3. And then we want to know, does that exceed the threshold that's required to make a spike, right? Our leak threshold. So that's another real number that we put into the system. So we want to see if this exceeds some value. Often people use theta because it's sort of like the first letter of threshold. And then, but to make it a little more uniform, we'll define a W0, which is the bias. It's often referred to as the bias instead of the threshold bias. And it's just the same as the threshold with a change in sign. And so then we can ask, is W0 plus W1 plus W3, is that greater than 0? And if that's greater than 0, then we'll be active. And if it's less than 0, we'll be inactive. And if we're thinking mathematically, we'll also wonder, well, what if it's exactly 0? This isn't really an issue for biology. With real numbers, there's never going to be exactly anything. But so we say, when we think, oh, you have to reach the threshold to be active, then we say, okay, if you reach 0, then you're active. So if you're greater than or equal to 0, you will be active. Okay, so this is often referred to as the McCulloch-Pitts model. They introduced this in the 1940s. And so they published this. In their original model, they had a different model of inhibition. So they proposed 2 alternate ways of treating inhibition. One is to use a negative weight, right? Because if you provide input at an inhibitory synapse, that will reduce the voltage if you're near the spiking threshold. And they also proposed an idea for inhibition, which was absolute inhibition, where if there's an inhibitory signal arriving, then it completely blocks that neuron from spiking. So with this, it was a little easier for them to design some of their circuits. They showed that it doesn't really matter which one you do. If you have one kind of neuron, if you have a neuron with absolute inhibition, then you can use those neurons to build a neuron that uses relative inhibition with a weight for inhibitory synapses, and the other way around also works. If you have relative inhibition, you can create neurons with absolute inhibition just by using very large negative weights. So after showing that it didn't matter which model you used, they preferred the absolute inhibition model because they were making a few very small circuits where you think about each individual unit, and so it was a little bit easier to think about it that way. But since then, pretty much everyone uses relative inhibition, and so in this model, we think of the weights as being positive or negative, and negative means it's inhibitory, and positive means it's excitatory, right? Because if you have a negative weight, then, right, if W2 is negative, then if this presynaptic neuron would become active, and this would change to a 1, then the sum here we would have to add W2 also into the sum, which is negative, so it would bring it down and make it less likely to reach the threshold. Okay, so this is McCulloch-Pitts neuron, and this basic idea that they came up with still underlies most of the very abstract neuron models that are used today. Okay, so let's think about how are these two things related, right? So there are these two worlds. There's the world of digital logic and the world of neurons. Well, this is some abstraction we have of the world of neurons. We hope that it has some relevance for helping us think about neurons. Just like this abstraction has relevance if we want to think about how to build circuits out of transistors, then this is very relevant. Okay, so we're hoping we'll learn something about how to build circuits out of neurons by studying these sorts of things. Okay, so first of all, suppose we have, so here was a very simple gate over here, just two inputs. It takes the OR. Can we do that same operation with this model here? Well, let's see how we would do it. We would let's do it for two inputs. So our two inputs are going to be 0 or 1. If right, when does an OR produce a 1 output? It produces 1 output if either input is 1. So so that means the inputs are probably excitatory, not inhibitory, right? Changing an input from 0 to 1 only makes it more likely that the output will be 1. It doesn't make it less likely. So we can try some positive weights, right? Let's say we have a weight of 5 and 5. And then what threshold would we need to reach? Well, if we consider the possible sums, right, let's call this input x1 and x2. So what can x1, right, we want to know 5x1 plus 5x2. x1 and x2 are both 0 or 1, right? And so when I write 5x1, what do I mean? I don't mean there are 5 inputs from neuron x1. What I mean is x1 is either 0 or 1, right? That presynaptic neuron is either inactive or active. If it's inactive, then it's not going to contribute anything to the, it's not going to affect the voltage in the cell. If it's inactive, x1 is 0. And so if we look at this term, if x1 is 0, this term is 0, it disappears. But if x1 is 1, if this input is active, then this term is 5. It's exactly the weight here. So this multiplying here is just a little trick to turn the active, which we encoded as 1, and inactive into the right value here. It's the weight. If the presynaptic neuron was active, this is 5, which is the weight. If the presynaptic neuron is inactive, then this product is 0, so it doesn't affect the sum. So that's the reason we multiply here. And then this is, whoops, this is the contribution from the other, from the second input. Here we have exactly the same thing, and then we're going to have some bias, right? So plus our bias. Well, let's think of it as a threshold for a second, as long as we're figuring it out. Let's we want to compare this to some threshold. So what threshold should we compare it to? Well, what can this sum be? So this sum, we can write this for the sum. It can be 0 if both of the presynaptic neurons are not active. It could be 5 if exactly one of the presynaptic neurons is active, or it could be 10 if they're both active, right? That's the biggest it could be with these particular weights. Why did I pick 5 and 5? Just to make an example. There's nothing special about 5. Okay, so when should the OR gate, when should it produce a 1? It should produce a 1 if any of the inputs are active. So already if we reach this level of 5, where at least one of the inputs is active, the output should be 1. So we can use a threshold somewhere between 0 and 5. Right, so let's choose a threshold of, right, we can choose a threshold of 3, for example, which means we can write W0 is -3, and so we can do this. And so this is an OR gate. And as you can see, there are many other values we could have put in here that would also make an OR gate, right? This could also have been -4, this 5 could be a 6, and so on, right? This 5 could be a 500, it would still work. Okay, so we don't have a good feeling yet for what this model can and can't do, but at least we can make an OR gate, right, out of a single unit here by setting all the weights appropriately. And in fact, if we want to make an AND gate, right, we're almost finished making an AND gate also. For an AND gate, it should only produce an output of 1 if both inputs are 1, right? So it needs to reach this high level of 10 for the sum. So the threshold should be somewhere between 5 and 10 for an AND gate. Right here for the OR gate, we had that can work with these values. There are many other possibilities also, but that way works. And for an AND gate, we can do something very similar. Should we just put a threshold, say, between 5 and 10? Okay, so we can also build AND gates, at least with 2 inputs. What if we have more inputs? What would we do? Actually, this very same idea works even with more inputs, right? We have, let's say we have 3 inputs. So then the biggest sum of the weights from these inputs would be 15. So now we would need a threshold between 10 and 15. So we could use a threshold, say, of 13, a bias of -13, and that would be an AND gate of 3 inputs. So we see we can have an AND gate of any number of inputs, and the same thing for an OR gate. For an OR gate, it's even easier, right? So here, we want to detect whether at least one of the inputs is 1. So that means actually still we need to look at the difference between 0 and 5. So we can just keep we don't even have to change the bias term. So we can do AND gates and OR gates with any number of inputs. How about a NOT gate? Can we do that? Because if we can do AND gates and OR gates and NOT gates, we know those are sufficient for building digital logic circuits. If we can build all of those with these units, then we would know that we can in fact build digital logic circuits with these units. Okay. So how would we build a NOT gate? A NOT gate, right, it has to produce the opposite of whatever its input was, right? The output is, if the input was 0, the output is 1. If the input was 1, the output is 0. So what does that mean? If the input wasn't active, then the neuron is active. It's just spontaneously active. But then if some input arrives, it turns off the neuron and the neuron stops being active. That means this input was inhibitory, right? It stopped the neuron from being active. And inhibitory inputs, our intuition says that should be a negative weight. So let's try a negative weight. We'll figure out the bias in a second. So let's use a negative weight. Right, there's only one input. We can say it has a weight of -5. Okay, so then what are the possible sums? So now these possible sums that we could get when we just have one input that can provide an inhibitory contribution, the possible sums are 0 or -5 now. Right? 0 if this input is not active, -5 if it is active. And so what's the threshold between those? Say -3, so we can have a bias of 3, let's say. And now, does this work? Well, yes. If we have, if our input is off, right, if x1 is 0, then the sum, I'll write it like, oops, I'll write it like this. The sum is, right, it's the bias term plus, oops, sorry, plus the first weight times the first input. right? So this, if x equals 0, then this equals, if x1 equals 0, then this is w0, which is, in our case, 3. And 3 is above 0, so the output, which so the output is going to be 1. And if we look at the opposite case, we'll see exactly the same thing in the other direction. Right? The sum is exactly the same, but now when we plug in x1, we get w0 plus w1, right, which is -2. So now we're below 0, so the neuron turns off. So this works. When there's no input, then the output is, then the unit will be active. If there is an active input, then the unit will become inactive. Okay, so we can make all of the digital logic gates. So we can create digital logic. And this was what McCulloch and Pitts showed, and they showed that therefore this general neuron model, we don't need different types of logic gates here. We can just use one generalized neuron model and set the weights differently in different units. And this is sufficient for doing all the amazing things that computers can do. Now, from a modern perspective, we no longer think that all the things we're able to make computers do is the same as all the things brains can do, right? Because we see that we have computers around us that are much faster than humans at doing calculations, but we still need humans to do almost everything, because the computers aren't able to do anything besides calculations very well. They aren't able to kind of figure out the most ordinary things that come up in regular life, right? So we'd like to build machines that could actually help us with those things. So we would still like to understand neurons, but just being able to do digital logic isn't enough. So let's try to understand what these neurons can do if we make circuits of these neurons. So what's an example of a circuit we could make? So for a circuit, we're going to have some kind of problem that takes several inputs, although even a single unit can take as many inputs as we like in either of these models. So having a lot of inputs doesn't require you to use multiple units. What would require you to use multiple units? Well, for digital logic, if you're doing anything besides and, or, and not, right? If you're doing something besides these, you're going to need multiple units, because a single unit is one of these units, and so that's all you're going to be able to do with a single unit. So for example, if you have two inputs and you want to test whether they're the same as each other, then none of these gates are doing that. So if you want to do that, you would need to build a circuit. And then how about with the neuron model? Would we be able to build, we have all this flexibility of setting the weights, would we be able to make a single unit that can tell if its two inputs are the same? So let's say we have two inputs, x1 and x2, right? And they feed into weight 1, weight 2, and weight 0. And then we have our output, let's call the output f. So it's like f of x1, x2. Could we design f? Could we create an equivalence detector? Could f be 1 exactly when the two inputs are the same? Well, we can try to do that, right? So if we consider that, actually there aren't many inputs we can provide to the system, right? If we consider x1 and x2, we can make a table of all the possibilities. They're each either, right? X1 is 0, and x2 could be 0, or right, each of them can only be 0 or 1, right? x1 is 0 or x1 is 1. And if x1 is 1, then x2 is either 0 or x2 is 1. And now we're done. There are only these 4 possibilities. So in each of these cases, what would f need to be? Well, we want it to be 1 whenever these 2 are equal. Right? So for an equality detector, we would have something like this. So is this possible? Well, f is f depends on this linear combination here, right? That we had here, this weighted sum of the weights, right? So if we take weight 1 times x1 plus weight 2 times x2 plus the bias, and then if we look at whether that's positive or negative, so we can use the sine function. So let's just define the sine of, when I write the sine function, what do I mean? I just mean it's 0 if x is less than 0, and it's 1 if x is greater than or equal to 0. Right, so it's just detecting if the value reached 0 or not. This is seeing if we reach the threshold. So f has this formula, and so each of these situations where we know the inputs and we know what output we want for those inputs, each of these situations corresponds to some equation with this formula. Right, so for example, here we have 1, f is 1 in the first row, is the sine of weight 1 times x1. Well, we know x1 is 0, so that term disappears. x2 is also 0, so that term disappears. Just the w0 stays. So that's the equation. I just left a lot of empty space to just so that the parts would line up. After I write a couple more equations, it's more clear. Okay, so we can write another equation. 0 should be the sine of, what do we have here? We have w1 is still 0, but now, sorry, x1 is still 0. See here, now in this case, we know the inputs and we're writing down the weights. We don't know the weights. We want to solve for the weights to design our neuron. So we're trying to figure out what weights would work. So in this case, the weighted sum is x2, is w2 plus w0. And so that should be negative, right? The sign should be 0. Right, and so we can do this for the others. And finally, the last one. Here, both of x1 and x2 are 1. And so we get, w1 plus w2 plus w0. Maybe I should put the w0 in the front, but it doesn't matter. Okay, so we have these 4 equations, and then we want to know, is there some solution? So, it's time for our break. Let's take our break. So we'll take our break now, and we'll resume at 9:15. Right? Okay. So see you in a few minutes.
Hi, Matt.
Hi, great. Okay.
Before we start, we have one question. It says, do we assume here in such a macular pitch model that all the input signals into a neuron have the same amplitude, the same current in case of input 1? And how does it correlate to the biological reality?
So in this abstraction, yes, we're making a big simplification with this 0-1 idea, this active-inactive idea. We aren't distinguishing between different firing rates. And this is the biggest thing that isn't quite right with this model. I mean, there are lots of things that aren't quite right if you get into the details. But even before getting very far into the details, this is something that has a problem right at the beginning. So yes, this model abstracts into just, it's as if every neuron that's active has the same firing rate, say 20 hertz, and then working from there. Of course, this isn't exactly true, so there are also more complicated models which we may, well, we won't go to very complicated models, but you can certainly get a little more complicated and include that. But for now, we're going to stick with this very simple idealization, just to see if we can even do something with this super simplified model. It's easy to make something very complex, and then you have no idea what it can do. That's easy, and it doesn't help, right? So we want to keep things super simple and see if we're able to figure anything out. And if we're able to figure things out, we can see maybe how we did it, and then maybe we can go to the more complicated model, right? It's like anytime you try to solve some new problem you don't know how to solve, first you try to solve a simplified version and so on. And so solving the brain is a problem we don't know how to solve. So we start with simplified versions and see what we can do. Okay, so I hope that answers the question.
We have a second question. How many logic gates do we need for simulating a neuron with n inputs? Because the person would assume it would somehow depend on how granular the input weights are, but it's not sure. So.
Yes, okay, so that's actually, that's a good question. It doesn't have a very clean answer. It has a it's a messy answer, and it's also in a class of questions that are typically very hard and don't have clean answers. But it's a good question, and we'll discuss some things that actually go in that kind of direction, where it's a little bit easier to talk about how many, right, comparing how big the circuits would need to be with these different kinds of units. Okay, so let's see. Oh, so we had almost figured out how to make a neuron that could detect this. We were solving for the weights.
You need to share your screen again.
Oh, whoops. Oh, that's a good point. Yeah. Boom, boom. Yeah. Good. Okay.
That's perfect. Yes.
Great. Okay. Yeah. So all I was saying, I was just pointing to this thing we were trying to figure out. Can we make a unit that can detect if its two inputs are equal? Right. That seems like a very simple task we might want it to do. So how would we do that? So we get these equations here, these four equations, but they have this sign function. So what does that mean? This sign always produces 0 or 1, right? We're defining it as just to be 0 for negative numbers and 1 for positive numbers, or also for 0. Okay, so this function, you can't invert this function, right? If you know that sine of x is 0, it doesn't tell you what x is. It just tells you x is negative, right? So we can't easily, so knowing that the sine of this thing is 1, right? We can't invert this. We can't solve for W0. All we know is that W0 has to be positive, right? Or 0. Okay, so let's write these four equations in that form. So here we know that W0 has to be at least 0. That comes from the first equation. So we're just going to take these four equations up above, and we're going to make four new equations, except they'll be inequalities, because really having the sign means that these equations just they're essentially inequalities. So for example, here where the sign is 0, that means this quantity has to be negative, right? So W2 plus W0 has to be negative. And this one, the next one also has to be negative. W1 plus W0 has to be negative. And then finally, the last one has to be positive, or 0. Okay, so now we have some inequalities. So how would we solve those? Well, we can combine inequalities, right? If we know that, for example, this is less than 0 and this is less than 0. So just like adding equations, we can add inequalities. If these things are both less than 0, then they're both negative. And if we add them up, it has to also be negative, right? So we can add these two, and we can get right. We get W1 plus W2 plus 2W0 is less than 0, right? And then we can do the same with the other ones. Right, here we have two numbers that are 0 or positive. So if we add them together, it also has to be positive for 0. So we get W1 plus W2 plus 2W0 is greater than or equal to 0. So now, right, we did these so that these quantities look, it's very nice that these quantities look the same. So now we can combine these somehow. Well, what can we do? Well, actually, we have a big problem, right? Something's not working, right? Because this quantity has to be positive or 0, but it also has to be negative. That's not possible, right? It doesn't matter what we plug in for the weights, for W0, W1, and W2. It doesn't matter what we plug in for those. We can't get both of these to be true. So what does that mean? Does it mean we found some contradiction in the universe? No, it means that it just was not true that there's a single function f that can, of this form, that can satisfy all 4 of these equations, right? These equations weren't consistent with each other. So trying to make a unit f, there is no set of weights that will make a unit detect whether its 2 inputs are equal or not. And in fact, we can see this at an intuitive level, right? So we did it through all these equations, and maybe you think, oh, okay, it's a lot of inequalities, but how would I ever know to do that? And how, what have we learned? Well, if we look back at our requirements for the problem, we can already see the problem there now that we have some idea of what the problem was. What was the problem? The problem was that things had to be negative, and they also had to be positive. These weights, somehow they had to be both, they had to add up to negative things and positive things at the same time. So it's like the weights had to be excitatory and inhibitory at the same time, which is not possible, right? So then, can we see that here? Yes, we can see that here. So for example, if we look at going from here to here, right? So say both inputs are off, but the output is active, and then we turn on the second input. Then what happened? What happened was the output went off. This means the second input has to be inhibitory, right? But what about here? Here, what happened was that right, we had the first input being active in both of these cases. The first input is steadily active, and then when the second input goes from being inactive to active, the output also goes from being inactive to active. That means that the second input has to be excitatory, right? But it's not, this isn't possible. We can't have this be inhibitory. The second input can't be both inhibitory and excitatory. And that's why it doesn't work. Right? And we could make the same argument for the first input also, right? So if we compare these two, we see the first input has to be inhibitory, and if we compare these two, we see the first input has to be excitatory. So this doesn't work on 2 levels. The second input needs to be both inhibitory and excitatory, and the first input needs to be both inhibitory and excitatory. So yeah, we can't do it with a single unit. But just like with and, or, and not gates, we can use multiple units to implement this function. With and, or, and not gates, you would also need multiple gates to do an equality detector. Now, what's kind of funny historically is that people, when they saw that a single neuron couldn't do operations like this, they thought, oh, this neuron model isn't very powerful, which it doesn't really make sense to think that, but people thought that for a long time. They thought, oh, these neurons, they can't really do very much because they can't solve even the simple problems. Well, that's true with a single neuron, but it's not true with a network. And since it's pretty clear that with the neuron model, you can implement all of digital logic, you shouldn't worry about what they can do. They can do everything digital logic can do. But somehow it took people a long time to understand this. So, so what's another way that we could think of this, right? So here I showed a way with equations, inequalities, right? Equations and inequalities. But we can draw a picture of what's going on. We can draw a graph. If we look at the input space, then there are 4 possible inputs, right? We can have x1 and x2 can both be 0. X1 can be 1. They can both be 1. Or just x2 could be 1 while x1 is 0. Right, so these are if we think about the input space with axes for the value of x1 and x2, then there are just these 4 possible inputs. It's the same as when we looked here. There are just 4 possible values that x1 and x2 can have because of this abstraction where we just write 1 for active and 0 for inactive, and there are no other values we consider. Okay, so now if we have x1 w1, I don't remember which way I usually write, or w1 x1 plus w2 x2 plus the bias. And then if this, right, we want to look at whether this is positive or negative. If this is what we're trying to think about, then what does that look like geometrically over in this picture? Well, this is the equation of a line, right? It's right, some linear combination of these, of x1 and x2, and then but here we're doing an inequality. So you probably had exercises like this in school. You just graph the line where it's equal to 0, and then on one side of that line it's less than 0, and on the other side of that line it's greater than 0. Right. So we can look at the discrimination line. And this will be some line in the space, depending on the well, maybe I should put it more instead of dots. I'll use another color, and I'll put it more to the so it's not going through a point. So that's an example of a line we could have, right? So this would be, say, for the line 2x1 plus 2x2 so minus 1 equals 0. It looks like about that line. So that's an example of a line corresponding to some particular values of the weights. And for other values of the weights, we would have a different line. So this line, if we have, if this side is the positive side and this side is the negative side, then this is exactly an OR gate, right? Because these 3 possibilities where at least one of x1 or x2, at least one of the inputs is 1, these all produce an output of 1. But the single input where x1 and x2 are both 0 produces an output of 0, right? And we can see that also in this formula, right? If at least one of x2 or x2 is 1, this will be positive. But if they're both 0, then this is negative. Okay, so this is what an OR gate looks like. And we can also draw an AND gate. And so this is a kind of nice way of visualizing things. And now let's consider the problem we were trying to solve previously. We were trying to make an example where we would distinguish these 2 points where the 2 inputs are equal from the other 2 points, from these 2 points where the inputs are not equal. And then we wanted to, we wanted to somehow distinguish those. And how can we do that? So if you think, well, where would you draw a line to separate the red points from the blue points? Well, it doesn't seem to work. But maybe we're just not creative enough, or maybe we don't remember our geometry very well. How can we be absolutely sure that there's no line? Maybe there's some funny line we haven't thought of that could divide it. It seems unlikely because this looks so simple. But how could we be sure there's no line that can divide the 2 of these from each other? Well, if we look at the 2 red points, they both have to lie on the positive side of the line, right? In order to be classified, in order for them to be classified as positive cases, cases where the output should be 1. So, and if both of these red points are on the same side of the line, then in fact, this whole segment between them has to be on the same side of the line, right? If the line would cross this segment here, then these 2 points would be on opposite sides of the line. But if the 2 points are on the same side of the line, then this whole segment has to be on the same side of the line, right? It doesn't matter if the line is over here or over here or over here. If the 2 points are on the same side, everything between them is also on the same side. This segment can't cross the line and then cross back to the other side because it's straight, and the line is also straight. Okay, so that has to be on one side of the line, and this, of course, has to be on the other side of the line. And now we see the problem. There's a problem right here. That's what's supposed to happen at the middle. And we're saying, well, maybe there's some workaround, right? We said the red had to be on one side of the line, but it could also be on the line because we use greater than or equal to 0. But it's still true. If the red points are on the same side or on the line, then the segment is also on the same side or on the line, whereas the blue one has to be completely off the line on the other side. So at that center point, there's a problem, and it doesn't work. And this center point is exactly what we found with the when we were looking at our inequalities, right? So these were the 2 red points, this case and this case, this case and this case. And when we added those up to get this inequality, adding them is pretty much the same as taking the average, which is like taking the midpoint geometrically, right? The adding them is 2 times the average. So if we would divide this by 2, we would have exactly the average, which would be the geometric midpoint of the 2 red points. And we did the same thing for the blue points. We took those 2 equations, we added them up. If we would divide by 2, that would be the average. So there we're saying exactly the midpoint has to be on the other side of the line. And so what we were doing with the inequalities is exactly the same as this geometric picture. Okay, and this geometric picture can give us some intuition of how we might try to find a solution to a problem, right? Suppose someone gives us right, say we have a lot of inputs, right? Maybe this is the x1 dimension and the x2 dimension and the x3 dimension. So that's a 3-dimensional picture. Maybe we make a 4-dimensional picture. And then we have, right, someone might tell us, oh, I want all of these points to be on one side of the line. Maybe I'll erase the 4th dimension for now because not everyone is happy thinking about 4-dimensional pictures. But it doesn't, everything works in any number of dimensions. So now we can imagine an ordinary 3-dimensional space. We have a bunch of points. And then maybe we have some red points and some blue points. And now, what would it mean for a line to divide these? Well, actually, in space, you would use a plane to divide the 2 halves of space from each other. So if you have an inequality in 3 dimensions, it corresponds to a plane dividing, right, the equation for the boundary where it equals 0 is the equation for a plane. And in general, if you have n dimensions, then the boundary is a hyperplane, which just means a space of one less dimension than the total number of dimensions. Right, so we used when we had 2 dimensions, we had a line to divide the 2 halves because it's one less dimension, and so on. So here, for example, we would be able to find some kind of plane that would divide these 2 sets of points, and this plane would correspond to some equation for right, there would be some W1 x1 plus W2 x2. When we think of it as a plane, then we would think of the weights as the coefficients, and x1, x2, x3 as the dimensions. Right, so the plane would have this equation. And in general, that's the equation of a hyperplane. Okay, so if someone wants us to find some weights to separate some 2 categories of points, sometimes it's not possible. Like in this case, it wasn't possible, but sometimes it's possible. Like in this case, it looks like it's going to be no problem, right? We can easily divide these 2 sets of points because the blue points are all over on one side and the red points are all over on the other side. So it's no problem. Okay, but if we have a bunch of dimensions, say we have 10 dimensions, and we have a bunch of red points and blue points, most of us can't picture 10 dimensions very well. And then we need to find 10 weights and a bias. So we need to solve for 11 values. And solving for numbers in terms of inequalities isn't the easiest. It's not the easiest type of problem. So here for this particular problem, we were able to work it out, but this was a pretty simple case, right, corresponding to a pretty simple picture. For more complicated cases, you need more complicated algorithms usually, but for this type of system we have here, there's actually a very simple algorithm that works anytime there's a solution. So for example, in this case, there is a solution, there's a plane here. So there's an algorithm that will find the solution whenever there's a solution, and the way the algorithm works is very simple. So this is called the Perceptron learning algorithm. So what's a perceptron? So a perceptron is just a circuit of these neural units, because when this is one of the early names used for making circuits of these units. So when you make a circuit of them, like, oh, I thought I had an example of a circuit here, but the only example circuit was of AND gates. But we can, if each of those AND gates was actually this unit that implements an AND gate, then we would have a circuit of these artificial neuron units. And so a perceptron is a certain form, and if the perceptron just has a single layer, if you think about layered networks, if each unit is just receiving inputs that are inputs to the whole problem, then you can just train each unit separately. You can design each unit separately to give the appropriate output, and so then this algorithm can be used. So this is, it's called a learning algorithm because it sets the weights. And when people talk about setting parameters in a system that's built out of units that are like neurons, then they call it learning. If they set parameters in a system that is just some abstract statistical set of equations, then they call it machine learning. But it's but this learning doesn't mean very much. You're setting a bunch of parameters, usually trying to optimize something. It's the same as optimization. Okay, so how would we do that in this case? So first of all, what are we being asked to do? So we have some examples, right? We have some example inputs. So if these are the inputs, then and we have some desired output. let's say desired, right? Then how can we set the weights? Right. Previously, we tried to solve for the weights. Here, we were trying to solve for the weights, but this algorithm doesn't solve for the weights. It starts with some set of weights. You just pick some random weights. They don't have to work at all, right? We can just start by guessing, right? Let's guess that weight 1 equals 3 and weight 2 equals, let's say it's inhibitory, and weight 3 equals 1. We could have a bias. These probably aren't very good weights. It looks like because of the bias, the sum is always going to be positive, even if this little inhibitory contribution comes. So these aren't good weights, but it doesn't matter. We can start with any weights at all. And then what we do is we look at the points that we're being asked to have on one side or the other of the hyperplane. So for example, let's say we want 0, 1, 1 to produce a 1. So I'm putting these ones in red. All of these ones should be on one side of the line. Right? Maybe they're just some, right? It's just some set of points. And there are also some points on the other side of the line. Maybe 0, 0, 0. Maybe if all the inputs are inactive, the unit should be inactive. And maybe if this unit is, maybe if both of these units are active, it should be inactive, right? So this is some set of requirements. Or maybe if just the last unit is active, maybe it should also be inactive, right? So this is some set of requirements. So this is the desired function. And so now what do? We have a guess for our weights. So we can just write this down as W0, W1, W2, W3. And we start out with 4, 3, -1, and 1. So now what do? We just try things, and we see when it works and when it doesn't work. So for example, we would try this first example. So if we plug in 0, 1, and 1 for x1, x2, and x3, then we're plugging in 0, 1, and 1. So for that one, then the sum would be 4, right? Because we have the bias term. This one doesn't matter because it's multiplied by 0, and these two cancel each other. So we get 4. And so this means that that the output of the unit is 1, which matches our desired output. So that's great. That's good. Okay, let's try another one. We can try 1, 0, 1. Right, that's the next one here. And let's see what output we get. So in that case, we would have, what would the sum be? We have 4. We always have 4. Then we get a contribution of 3 that brings it up to 7. We ignore this because of the 0, and then the 1 makes it be an 8. So the sum is 8. F out is 1. And again, that's great. It worked. Okay, let's try one of the blue examples. So here, if we plug in 0, 0, 0, then what is the sum going to be? Well, then that's easy. The sum is 4 because everything gets all the weights get multiplied by 0. Okay, so this means F out, right? The output of the unit is 1, and that's not good because the output was supposed to be 0. So something went wrong. What went wrong? Well, let's not think about it very hard, right? This is just an algorithm. An algorithm means some set of steps. You don't have to think, you just have to follow the instructions. Okay, so what should we do? But let's think, to understand what the algorithm is, let's think for a second. How could, right, our sum was too high. How could we reduce the sum? Well, in fact, none of these terms contributed, only the bias contributed. So we need to reduce the bias. So what we're going to do is we're going to subtract 1 from the bias. Why 1? Well, it's just, you can subtract whatever you want, but 1, if we always subtract 1, then it's that's the simplest thing we could do. So then we're going to have the terms 3, 3, minus 1, 1. And actually, we can see if we plug in the same thing again, we're going to have the same problem. We've only reduced the sum to 3. It's not enough. We need to keep reducing the sum. It will keep going down. We'll need to subtract 1 a few more times, down to 0, even another time down to minus 1. And now we have a sum of minus 1, which means our output is finally 0. And so this is finally correct. So that's good. So we fixed this one. And that's also when we think about learning, when people talk about learning as a form of optimization, learning is a type of optimization where you have a guess and you try to improve it. So you might do this by following a gradient. You might do it in some other way. Here we're doing it in a, well, it seems like we still had to think a little bit, but we'll see in a second that here we're doing it in a very simple procedural way. So how can we do that? Okay, let's look at what we were doing here. Well, let's do one more example, and then we can maybe see a little more clearly. So our next example, we have 1, 1, 0, and then we have the sum. Now, what's the sum in this case? We have the sum. Well, we have a bias of minus 1. We add 3. Yep. We have that brings it up to 2. We subtract 1, it brings it down to 1. So the sum is still going to be 1, which means the output is 1, right? It's positive, and this is not so good. And so what can we do? So now, to bring down the sum, we can reduce the bias. But it's also good to bring down these weights, because these weights, because of these 1s, these weights were contributing. So we can reduce all of those. So so we're going to reduce all of these places where there was a 1 in the input. Of course, where there was a 0, we don't worry about it. We just let it. We don't change that weight because that weight had nothing to do with the sum being wrong. Okay, so now we have minus 1, no, sorry, minus 2, 2, minus 2, 1. And now if we try that same example, 1, 1, 0, then we get the sum is minus 2 plus 2 minus 2, and this one doesn't contribute. So that's a total of minus 2. And now this one is correct also. So we made them correct. Now, in changing these weights, we might have messed up some of the earlier examples. So what this algorithm does is it just keeps going from example to example, trying to fix individual examples, and it just keeps cycling around. And the interesting thing about this algorithm is eventually this process will succeed. It will find a set of weights that work, which isn't obvious at the beginning. Okay, so let's look a little bit at what's going on here. When we changed these weights here, we subtracted 1 from all 3 of these. Here we subtracted 1 from just the first one. So in general, we're subtracting 1 from anywhere where the input was a was a 1, and we're also subtracting 1 from the bias. Now let's do something a little bit funny. Let's pretend there's a fourth input. Let's suppose there's an input x0, which always equals 1. Why do we do that? Just because it makes our calculations here a little bit more uniform. So here, for example, we're multiplying the weights by the inputs, but then we just had this extra W0 hanging out, right? It didn't get multiplied by an input, but now we can multiply W0 by X0, which is always 1, right? That's a definition of X0. It's just always going to be equal to 1. And so that means that we can write our sum of weights as X0 times W0 plus X1 times W1 plus X2 times W2 plus X3 times W3. You get the idea. And in fact, this type of combining of two things is exactly how you do a scalar product or a dot product, right? Those are the same thing. So if you have a vector X, which is given by X0, X1, X2, and X3, and you have a vector W given by W0, W1, W2, W3, then this sum is exactly the dot product of these two vectors. It's a scalar product, right? So, so some people will write it like this. So depending on what educational system you went to, you'll have probably seen one of these two ways of writing it. But these are exactly the same thing. It's just different notation. Okay, so so that's kind of nice. We have a way of thinking about the operation we're doing instead of, right? We've simplified our thinking. Even if it's in a large number of dimensions, all we're doing is we're looking at this scalar product of two vectors. And what is the scalar product of two vectors? Geometrically speaking, so in a geometric picture, the scalar product is given by the lengths of the two vectors multiplied by the cosine of the angle between them. So it has a geometrical meaning. Right, so this is the length of one vector times the length of the other vector times the cosine of the angle between them. And this angle, this angle in 2 dimensions, you can think of it as an angle. In 3 dimensions, it's also just an angle between two vectors. In fact, in any number of dimensions, it's just an angle between two vectors. The angle, those two vectors lie in some plane. So the way we think about, the way we draw diagrams on a piece of paper is completely sufficient for thinking about the angle between them. And the angle has to be, it's something from 0 to 2 pi, 0 to 360 degrees, actually to 180 degrees, because after you go past 180 degrees, you're actually you're going back down to 0 again for the angle. So it's something between 0 and 180 degrees, and so right, we write 0 degrees less than, right, alpha is somewhere in this range, and cosine of alpha, right? If you imagine the cosine function, it looks right. It looks something like this. This is pi. This is 180 degrees, and the cosine is positive. when this angle is between 0 degrees and 90 degrees. Sorry. And it's negative for larger angles, right? When and why do we care when it's positive or negative? Because actually, if we look at these two terms, these are always positive, right? The length of a vector can't be negative. It's the absolute value. It's the length. It's the size of the vector. So these are both positive. The vectors aren't going to be 0. The weights, well, maybe the weights could start at 0, but they quickly won't be 0. And the input vector, because x0 is always 1, the input vector is also not, it won't have length 0. So these are both positive. And so the sign of this is determined by the sign of the cosine, whether the cosine is positive or negative. And the sign of that being, sign meaning positive or negative, is interesting because that's what we wanted to know about this whole expression. Is it positive or negative, right? We wanted to know, is it, we want it to be less than 0 on one side, greater than 0 on the other side, right? So we care exactly about the, whether that's positive or negative. And so whether this is positive or negative, right? Whether this is positive or negative depends just on this cosine. It depends just on the angle between the vectors. So geometrically speaking, there's a very nice way of thinking about what the about how this formula for what this artificial neuron unit is doing is related to the geometry, for how those two things are related. Okay, so so to close up, where are we now? So with this algorithm, okay, I just have to say one final thing that I almost said here. If we include this x0, right? Let's we can write it here. If we always include this 1 as the first input, then we can see that what we're doing each time we make an adjustment, we're subtracting this input vector. So we subtracted this input vector x from our weight vector. Right, there's the weight vector. And here we subtracted that. And then, right, so then our new weight vector was our old weight vector, and we subtracted the input vector. Right, we just subtracted it here. And then the same thing here, down here, again, we subtracted this, another input vector. This is another input vector for another data point. And we got, right, we subtracted it in pink, and we got this, again, an updated weight vector. And so we're always updating the weight vector with the input vector. And this is what the perceptron learning algorithm does. When the, if you had a blue example that didn't work, you subtract the input vector. If you had a red example, we didn't have a case like that, but if you have a red example that didn't work, you need to raise this value, you need to raise the sum, and so then you add the input vector. And so by adding or subtracting the input vector, we slowly change the weight vector. And what are we doing? We're making the we're adding input vectors for these red points. These red points are the input vectors we might add, and the blue points are the input vectors we might subtract. And so after we've added a bunch of these and subtracted a bunch of these, it's like we have a big vector pointing from this towards that. And that vector, by the formula for a plane, is the normal to the plane, and that puts our plane into the right position. And so that's the geometric intuition of this algorithm. We can also prove that the algorithm converges, but we are out of time. So we may look at that next week. But I just want you to realize that by making this abstraction, this extremely simplified neuron, we're able to connect to solving equations, we're able to connect to geometry, we're able to start using our intuition to try to think, oh, okay, how is the neuron trying to learn and get better at what it's doing? And so that's the point of making such an extremely simplified model. Okay, we'll continue next week.
Thank you, Matt. We're gonna have a break and then we're gonna come back for the exercise sessions like 10:15 again.
Yes,
Thank
sounds
you.
perfect. Okay. So today there were two exercises. I will quickly go through both of them. Okay. I think, Vanessa, I think it's easier if you interrupt me if there are any questions. Is it okay?
Yeah, sure. I will do it.
Good. So, as I said, there are two questions. The first exercise was about spike timing dependent plasticity, and you were given this plot. And on the x-axis of this plot, you have...
Mateo, do you
Yes?
have anything to share on the screen or?
Oh, yes.
Okay.
Apologies, I started the presentation without sharing the screen.
No problem.
Okay. Apologies for that. Thanks. Good catch. Exercise 1 was about spike timing dependent plasticity, and you were given this plot, which so on the x-axis you have delta t between a pre and a post synaptic event. So a negative time in milliseconds means that the presynaptic spike arrives before the postsynaptic spike, and a positive value means that the postsynaptic spike is before the pre. And then on the y-axis, you have delta W over W in percentage, which is the amplitude of excitatory postsynaptic current. So how much a single synapse contributes to the postsynaptic neuron. And you can see this as kind of the strength of the synapse. So question number 1 is, why is it important for any learning rule to have mechanisms for both the strengthening and the weakening of synaptic weights? And to answer this question, we can just think of a scenario in which we only have strengthening. And in a scenario like that, then all the weights would explode, would become massively big, and the network would become unstable. It would cause basically everything to fire, and this would basically lead to epilepsy. So having inhibition and weakening of synaptic weights helps us normalize the inputs and helps us balance the network in order to work efficiently. So point number 2. So given this, given the plot that I just explained, f of delta t is the amount of synaptic weight modification observed after a pair of pre-post synaptic spikes as a function of delta t. We went over this, and the equation that governs this plot is given here. And we need to estimate the parameters of a plus and tau plus for the function f. So to understand the value of a plus, we can evaluate this function at the time where delta t is 0. So can you see my cursor? So when delta t is 0, we have that the function is 0.5. And we know that the exponential of 0 is 1. And so we can safely say that a plus will be 0.5 due to the fact that the function returns 0.5 and the exponential of delta t is 0, hence this will happen. And then to calculate the tau plus, we're still on this curve, and then we can look on the curve, and we have that for a value of -20 milliseconds, we have that the function value is 0.2. And so then we can plug in the numbers in the equation. And this will yield that tau plus is 21.8 milliseconds. So I'm just using this function here, this equation here, and I'm just plugging in. And so we have that f is 0.2, and that delta t is -20. Okay. Are there no questions? All good so far?
Yeah, no questions so far.
Exercise 3, if two neurons fire completely independently, there are on average as many occurrences where the first one spikes just before the second one does as the opposite case. So when the second one fires before the first one. Nevertheless, a synapse between two such neurons would be weakened, which will only happen if the integral of the function f is negative. Draw a weight update function similar to the figure shown that ensures the uncorrelated pre-post spikes produce an overall weakening of the synapse. And to do this, we need to modify either a minus or time minus. And so we can get this plot in two different ways. And basically what needs to be done is that the area under the curve in the positive part of delta t, so when the post is before the pre, the pre before the post is larger. So a larger area under this curve will imply that the integral will be negative. And so it will, if the spiking is uncorrelated, then it will produce an overall weakening of the synapse. Okay, so far so good. And then exercise 4 was very, was quite long and some reasoning involved. Basically, it says, so it has 3 different points. When excitation is strong so that the mean input of the neuron would bring it well above threshold, the neuron operates in an input averaging or regular firing mode. Its firing rate is approximately the inverse of the refractory period. Hence, the precise timing of its individual action potentials is driven by internal dynamics and fairly insensitive to presynaptic spikes. In a plot like this one, where the x-axis describes the time difference between pre and post, how are the spikes of a neuron in that regime distributed? So if it's firing at its maximum, if they're both firing at their maximum firing rate, this plot will just be a uniform distribution across all delta t's, because you're not forcing the, there is no correlation between the pre and the post. So, and then the next point is, given this distribution, what is the requirement on the STDP modification function that guarantees that a synapse will be weakened in this situation? And basically, the condition for that is that the integral of this uniform distribution has to be negative. And so,
Matteo?
Yes?
There is a question, and also when delta is positive, you have that? Even when the difference is positive, or just?
So it would be a uniform, yes, that's exactly what so we would have probably a uniform distribution here, and then a uniform distribution down here. And we want that so that the STDP be, so that the last point is successfully answered. We want that the height of the negative part is greater than the height of the positive part, so that the overall integral is negative, and so that it'll have weakening, general weakening. The second point was, when the excitatory synapses are weakened by STDP, the postsynaptic neuron enters a balanced mode of operation, in which it generates a more irregular sequence of action potentials that are more tightly correlated with the presynaptic spikes that evokes them. The total synaptic input in the balanced mode is on average near or below threshold. So the postsynaptic neuron fires irregularly, primarily in response to statistical fluctuations in the total input. On a plot like this one gives like the given one, where the x-axis describes the time difference delta t between pre and post synaptic firing. How are the spikes of the neuron in this regime distributed? So in this balanced mode, we are in a scenario where an action potential, so a post-synaptic spike, occurs for fluctuations of many different input spikes. So there tend to be more input spikes than an output spikes. And so the presynaptic spike, and so the weights will tend to become more positive, because on average, you will have more synaptic, for many pre, you will have one post. And so you will be in the left side of the curve. Right? I mean, I hope that makes sense. And so the weights will be potentiated. And finally, is it possible to draw an STDP modification function for which synapses in the first regime are weakened, but synapses in the second regime are strengthened? Why would such a learning rule be useful? What we're looking for is that we want a scenario in which firing activity will, like the first case we saw, will weaken the synapse, but a balanced network will strengthen the synapses. And the solution of this is mean field output activity of the output neuron. And so just looking at the output neuron and its mean firing rate, we should be able to determine what happens. If it fires at a high firing rate, it will probably be weakened. If it's a more balanced state, it will be strengthened. And so this leads us to exercise 2, which is called predictive coding with STDP. So we're still using the exact same learning rule as we saw before. In this case, we have an input, I1 that goes on N1, I2 that goes on N2, and then 2 synapses, S1 and S2, that connect N1 to N2. And yes?
Nothing, sorry, just someone that passed.
Sorry. What effect do you expect at synapses S1 and S2 due to STDP, and why? Plot the development. Okay, so the protocol we're giving here is we're giving input 1 and then we're giving input 2, one after the other. And so we expect neuron 1 to fire before neuron 2. And so knowing this and knowing the STDP profile, we should be able to plot a plot like this, in which synapse 1 strengthens and synapse 2 weakens. So in the beginning, they will be the same, and slowly synapse 1 will strengthen even more, and synapse 2 will keep depressing. This is because of how we're giving the input. So we're giving input 1, waiting 5 milliseconds, giving input 2. And so neuron 1 will fire before neuron 2. If we were to do the opposite, then synapse 2 would be strengthened and synapse 1 would be depressed. Explain how the spiking pattern of N2 and I2 in response of the stimulus sequence changes over time. How does the network react after learning if only input 1 but not input 2 is presented for a single trial? And so in the beginning, I2 fires before N2 and therefore causes N2 to fire. After learning, however, S1, so the synapse from neuron 1, is strong enough to excite neuron 2, which in turn inhibits input 2. So input 2 cannot cause I2 to fire anymore. And this, if you look at the previous plot, this plot here, you will see that after a certain number of trials, S1 will be very strong, and so will cause N2 to fire, which will inhibit input 2. How would the network after learning react if the inhibitory connections were removed? Okay, so if we remove these inhibitory connections, we would basically not have this inhibition of input 2, right? And so without the inhibitory connection, input N2 would fire twice, once because it is stimulated by N1, and a second time for the actual input of N2. And then finally, I think this is the last point, Assume that instead of STDP, a temporally symmetric Hebbian learning rule was used, which potentiates synapses whenever the pre and post neuron fire together within a short time interval, regardless of the order of which the spikes arrive. What problem would you expect in such a network? And this is similar to, yes, wait, let me finish this and then, this is similar to what we saw in exercise 9.1, in which both S1 and S2 would be potentiated. And so there would be no way of learning causality, like what comes first, what triggers what. And then the network would become kind of unstable. So I think this was a fairly short exercise session, just 2 exercises. I think they are quick exercises, but they are very targeted to understanding how neurons and synapses work. And so if you understood these easily, then you should be on the good path, I think. Yes, Vanessa.
There is just one question. What is the propagation time from synapse to synapse?
That's a good question. I would have to double check to be perfectly sure. I know that in exercise 8, there was an example about this. I would say 0.8 milliseconds. So think about what needs to happen. So you have a presynaptic spike. It goes into the synaptic bouton. It will trigger a cascade of events, which has to release a neurotransmitter. The neurotransmitter needs to propagate. It needs to attach to the postsynaptic, and then it will trigger. So it's in the order of less than a millisecond, but it's not instantaneous at all. And then keep in mind, this needs to then propagate to the soma of the postsynaptic neuron. So there are many nonlinearities that happen. But yes, I think 1 millisecond or a little below 1 millisecond is a good approximation.
Okay, there are other questions. So regarding inhibition, for how long do we assume the inhibition holds? Because we assume that N2 inhibits I2 when it comes, but we ignore the part of the inhibition of I1.
That's a good point. So in the header of the exercise, there was written that the protocol that we're using is input 1, we wait 5 milliseconds, input 2, then we reset everything, and then we redo it. So this is why we don't consider that N1 will inhibit input 1. In a real life scenario, I agree, that is an issue. Yeah, that's a good question. But this exercise was more targeted on something else. In real life, inhibition, that's a good question. I don't know for how long it holds. I would say a few milliseconds. It's kind of, you can see inhibition as a negative current, right? And so all the properties that we've been talking about for excitatory are kind of the same for inhibitory. And so, instead of an excitatory postsynaptic current, you will have an inhibitory postsynaptic current that will take current away from the soma. It also depends where the dendritic, axon dendritic synapse happens. So if it's very far away, the inhibition will have a much less effect. But if the inhibitory synapse attaches directly to the soma, then it will have a very big effect. So we can call that shunting inhibition. So, yes.
Okay, there's another question. I think it's basically the same as well. In the exercise 9.2, the input 1 doesn't get inhibited by S2 in the graph. Is it because I1 fires before I2? I think it's just because the definition of the exercise, right?
We can. So in the exercise, can you still see my screen?
Yes.
So assume that the network is stimulated repeatedly by an input sequence in which first only input 1 is present and then only input 2 after a 5 millisecond delay, the time between each presentation of the sequence is long enough not to influence plasticity. So basically what we're doing is we're resetting everything and reapplying the same protocol.
There is another question saying, so when N1 fires before N2, S1 will be strengthened?
True. Yes.
And another one saying, could you maybe explain why we have first linear growth of the synaptic strength and then non-linear in the plot for solution 9.21?
Wait, can you repeat that? What, 9.
Why we have, oh, so there wasn't the plot before.
Yes. Yes.
Yeah, 9.2, yes, this one. Why it is like linear and then non-linear?
I mean, in principle, even had you drawn it linearly, it would have been good. It's just it keeps moving by if we use this plot here, it'll keep moving by let's say fixed. That's a good question. I think it keeps moving by kind of a fixed percentage, and so it should. That's a good question. Maybe I made a mistake. I'll look into it. I don't want to say something wrong. I'll make a mistake.
Okay, I don't see any more questions in the chat now.
Okay. Wonderful. So we can still be here for a few minutes. And then if anyone has any questions, let us know. If not, we can.
Yeah, and I'm gonna upload the exercise of the lecture of today later.
Yes. I also uploaded. I uploaded the solutions as well of this exercise as well.
Cool. Thank you, Matteo.
Thank you, Vanessa.
Okay, so there's a question. Could you explain again what we do in 9.1 part 4 in the last question?
Of course. So so assume that instead of STDP, a temporally symmetric Hebbian learning rule was used. And a temporally symmetric Hebbian learning rule just means that instead of this plot here, you flip the x-axis above. And so you have two symmetric curves that both potentiate. And so at this point, you will potentiate regardless of pre coming before post or post coming before pre. Right? And so in doing so, you will lose the information whether the pre came 5-10 milliseconds before the post, or if the pre came 5-10 milliseconds after the post. And so you will have no information about any causality, any A causes B or B causes A. And if in the end it's all the same, then you cannot reconstruct what happens. Does it make sense? So maybe I should have specified it better. A symmetric Hebbian learning rule would be flipping this this curve, so the curve that weakens the synapses over the x-axis, and so it would be symmetric in a positive way.
So they're saying this is 9.2, but I see 9.1 on your slide, but they meant 9.1, the exercise 9.1.
Okay. What about exercise 9.1?
So I think, yeah, so question 4, I guess, last question of 9.1. Yeah, number 4, 9.1. That was, yeah.
Okay, I can try go over it again, but it's quite long. Okay, so now consider how STDP synapse will behave in two different operational regimes of the postsynaptic neuron: regular firing mode and balanced mode. So when excitation is strong, so that the mean input of the neuron would bring it well above threshold, the neuron operates in an input averaging or regular firing mode. Its firing rate is approximately the inverse of its refractory period. Hence, the precise timing of its individual action potentials is driven by internal dynamics and fairly insensitive to presynaptic spike times. On a plot like the given one, where the x-axis describes time difference between pre and post-synaptic firing, how are the spikes of a neuron in this regime distributed? So the spikes would be distributed uniformly. So we're talking about just, so we're not asking how would the weight be updated. We're asking how would the delta t plot look like. And that, since they're both firing at kind of a same frequency, or I don't know if it's the same frequency, but maximally and kind of in a not really correlated manner, it would just be a uniform distribution over all delta t's, because the probability of them spiking together is the same as the probability of them spiking 10 milliseconds apart. Given this distribution, what is the requirement on the STDP modification function that guarantees that a synapse will be weakened in this situation? And so the answer to that is basically we need to make sure that the STDP profile, so this profile here that is an exercise 9.1, the integral of all of this is negative. And so if the integral of all of that is negative, then we will be fairly sure that the synapse will be weakened. Yes, Vanessa?
So there's a specific question saying, how do we strengthen the balanced while weakening the regular one?
Okay, so that's, if I remember correctly, that should be exercise 3. Is it possible to draw an STDP modification function for which synapses in the first regime are weakened, but synapses in the second regime are strengthened? Why would such a learning rule be useful? Okay, wait, let me, yes, so the, in order to have the firing, so we're just looking at the postsynaptic solution, and the solution is looking at the mean output activity of the output neuron. If it will fire a lot, then it will be probably weakened because we're in this regime here. So if the postsynaptic fires a lot, then we will most likely be in the right side of the plane because this is when the post comes before the pre, right? However, if the postsynaptic neuron fires very sparsely, and so it needs many presynaptic inputs to trigger postsynaptic action potential, then we're in the left side of the plane in which a lot of pre fires before post. So I hope this is kind of a subtle thing that doesn't come out of equations. You just kind of have to reason through it, right? Because so if you're firing maximally, then you have a lot of activity, and so you have a lot of post activity, and so this will cause weakening. Well, if you're very sparse, then your input is much more important, and so it will potentiate. If it's still unclear, I can try and explain it again.
Yeah, it's clear now.
Good.
Any other questions or?
don't apologize for the misunderstanding. I'm happy to re-explain it.
Yeah, okay, I think then that's it.
Perfect. So yeah, so next week I think Vanessa will do exercises.
Yes, correct.
Good. And yeah, have a good rest of the week.
Yes, okay, thank you all. See you next week. Ciao.
Ciao.